Hi, I'm David Bonsack, Global Marketing Manager at TA Instruments. I'd like to welcome you and thank you for joining us for today's webinar. During the webinar, you can customize your viewing interface by rearranging the windows to your liking. You can also resize the slide and video windows independently of one another by clicking and dragging the bottom right-hand corner of either window. If you get disconnected at any time, use the instructions you received to log back in. You can access additional content through the widgets at the bottom of the screen. These include speaker bios and helpful additional resource downloads. If you need help at any time, click the question mark widget. Submit any questions you have through the Q&A window. We'll do our best to answer as many as possible at the end of the webinar. Our guest speaker today is Dr. Martin Centmanat. Dr. Centmanat is the founder of Expansion Instruments, the exclusive manufacturer of his invention, the SER Universal Testing Platform for Extensional Rheology Measurements. Dr. Centmanat received his bachelor's degree in mechanical engineering from Texas A&M University and his master's and PhD in chemical engineering from McGill University in Montreal under the instruction of Professor John Deely. It is a pleasure to have Dr. Centmanat with us today. The title of his webinar is Extensional Rheology, an invaluable tool for material characterization. Martin?
Thank you very much for that introduction. Today I'll be talking about extensional rheology. In particular, how extensional rheology can be used as an analytical tool for material characterization. Many of you know what rheology is, but just as a refresher, rheology is the branch of physics that deals with the deformation and flow of matter. Now, it's the goal of any rheologist to relate the rheological properties of a material measured in the laboratory to its molecular structure or architecture. This is done so that we can gain fundamental insight into material deformation behavior. We can develop constitutive models then that embody these fundamental structure property relationships. And ultimately, we can predict now how newly developed materials will behave to applied deformations during processing and end product use. It's really the goal of a rheologist to understand the material behavior, not just when it's in a molten state or fluid state, but when it's in a solid state. So it's really our objective to understand materials from processing, raw material, all the way to end product use in its solid state. Now today I will be focusing on extensional rheology. And for those of you who aren't familiar, extensional flow refers to a type of flow deformation that involves the elongation or stretching of material. And it's the type of flow that dominates many polymer processing operations, from film blowing to injection molding to extrusion. There are many facets associated with extensional rheology that will dictate and dominate many of the instabilities that occur during these processing operations. Crystallization kinetics and final morphology are deeply affected by molecular orientation and stretch induced by flow during polymer processing. Extensional flow measurements are also very useful in polymer characterization because they generate high molecular stretch and orientation flow fields and are very sensitive to the molecular structure of a polymeric system, and they are ideal for characterizing the flow-induced crystallization behavior of polymer melts. Now, uniaxial extension is actually the strongest flow field we can generate as man. As a consequence, due to that really high degree of orientation and stretch that we can achieve actually a preferred packing structure so that during this deformation, this uniaxial deformation, we actually can induce a crystallization kinetics reaction when we're close enough in temperature to the crystallization temperature of that material. Now today I'll be focusing on a technology that is used now pretty commonly in the field of rheology for characterizing extensional rheological flows. That is SER technology. The SER Universal Testing Platform is a device that I invented and pioneered, and it's actually a miniature detachable fixture that can be used on a conventional constant stress rheometer as well as a controlled rate rheometer. It's actually can convert that rotational rheometer system really into a universal testing platform. So it can do more than just rheology. It can do basically anything now a typical universal testing apparatus like an instron can do, but it rates orders of magnitude higher. This really is a really key feature to keep in mind, because the devices that we use as these host stations are incredible machines. They really are untouchable in the material characterization community in terms of capabilities, what they can achieve in terms of rates and resolutions in terms of load sensing is really is unparalleled. So what happens with the SER is that we actually translate that really nice precision rotational motion into a very nice linear motion. And by utilizing these counter-rotating wind-up drums, as we'll see here shortly, we can achieve linear deformations that are very precisely controlled in a fixed plane of orientation, which can be viewed at all times within the material deformation process. So whether you're talking about extensional rheology, peel adhesion testing, tensile testing, tear testing, or fracture testing, these are all the different types of material deformation modes that can be achieved with the SER universal testing platform. Now this is how it works. As I explained, that you can basically have this detachable fixture on your rotational rheometer. So it would attach up to your motor head as you would normally have a fixture attached to the spindle. And this rotational motion of the rheometer spindle drives the counter rotation of the dual wind-up drum. So as you can see, you can attach the drive shaft of the SER, as you can see in the diagram, to the motor transducer spindle. That motion drives the motion of the drive shaft. You can see there's a little universal joint that allows for a significant degree of misalignment, should there be any. And then it drives the main axis of the SER, and you'll see that there's intermeshing gears there. And so the rotation of the primary drum drives the rotation of the secondary drum. And in this manner, we can achieve a very nice translation of rotational motion to a linear motion as a material is now attached to the surface of the drums. So you can see here that as a sample is attached to the surfaces, it experiences a controlled linear deformation within the confines of the oven enclosure. So again, in this very nice, succinct, and compact manner, we can achieve very large deformations as a function of temperature and the entire scale of rates, as well as torque sensing capabilities. Very powerful technique. Now, obviously, with any new development or any type of extensional measurement or a rheological measurement, we'd like to be able to measure and verify the type of deformation that we're actually applying. In this particular case here, I've shown an actual video of a material being deformed. In this case, it's actually an elastomer. And I've superposed now as a yellow box what the theoretical width evolution should be just based on rotational motion of the drums. And now I've superposed that theoretical width evolution over the actual image so we can see how closely it translates. And you can see that we achieve very good control all the way up to sample rupture. So you just see it again. You can see here that we can achieve all the way up to sample rupture. We have a very good control of our strain deformation. Now, even though we have a number of different capabilities in terms of material deformation behavior, today we're going to be focusing exclusively on extensional rheology. There will be another facet that we'll be talking about, another capability with the SER, and that is in the peel adhesion category of material deformation. But for the most part, we're going to be focusing on extensional rheology in this talk. Now, what's really neat about this technology is that you can use very, very small samples. So if you're familiar with other devices that have been used for extensional rheology in the past and historically, we're able to use very, very small sample sizes. We can achieve very good and uniform controlled deformation, as well as, because it's so small and everything fits within the environmental oven chamber, we can take advantage of the very good temperature control that these rotational rheometers can achieve. And as a consequence, now we have an ideal system for measuring the properties of a material as a function of temperature. As we can see here, another sample that's being deformed. Again, we have clear visibility of that sample during the entire deformation process. Okay, so to start off, to get familiarized with extensional rheology, we're going to start off with a couple of different looks at flow-induced crystallization. It's a topic that's very, very important in polymer processing because it is typically during this process that we lock in the morphology associated with the crystallization, the solid state behavior now of that material and the end product. In this particular case, we're going to be looking at two different material systems. The first is a butyl rubber, and the second is a linear polyethylene. And we're going to be looking at tensile stress growth and cessation of uniaxial extension, as well as looking at bubble instability and uniaxial extension and flow birefringence. So starting with butyl. If you're unfamiliar with butyl, it's a really unique material. It's actually a copolymer of isobutylene and a small amount of isoprene. And actually, typically, the amount of isoprene is only on the order of about 2%. But as you'll see, that 2% can have a dramatic effect on its end properties, particularly its material deformation behavior. Now, butyl is a material that is used almost exclusively by the rubber and tire industry. It is actually the layer of material that comprises the innermost layer of your tire. Without butyl, your tire would not be able to maintain its air pressure. The diffusion coefficient for air through natural rubber and other synthetic rubbers is actually fairly high, but butyl has a very low gas permeability. As a consequence, that material compound is what keeps the air in your tires. Now, as a consequence, though, because of this gas impermeability, it can also develop voids. Air bubbles, if you can imagine, during processing will be entrapped because, again, it's such a good air barrier. During processing, you can actually entrap a lot of air bubbles during the material deformation. So let's take a look, first of all, at tensile stress growth of butyl. This is now at an elevated temperature of 50 degrees Celsius. So it's typically around the temperature that you'd be processing this type of material. And you can see here that what we do in a tensile stress growth curve is we're plotting the transient extensional viscosity. So it's the instantaneous extensional viscosity as a function of time. And it's typically represented on a log-log scale. And as we can see here, we've plotted for a various number of rates from 0.001 reciprocal seconds in Henke strain rate units all the way up to 30 reciprocal seconds. Now, for those of you who aren't familiar with Henke strains and Henke strain rates, it's actually the true strain and true strain rate that we're talking about here, not the engineering strain that you typically are talking about when you're talking about types of dog bone type of elongations. So now we're talking about true strains. That's an important thing to keep in mind because since we're talking about the deformation of fluid materials, the deformations that are associated with fluid flow is enormously large, much larger than that's achieved with solid materials. So even though it's easy enough and simple enough to calculate engineering strains when you're doing an instron type measurement, because the deformations are relatively small, there's really no deviation or no error that's introduced by using an engineering strain calculation. But now as you start going to very, very large deformations, it's important to keep everything in terms of a true strain, or as we also refer to it here in the extensional rheology community as the Henke strain. So you can see here at 50 degrees Celsius, we have a material behavior that is very, very linear-like, as that is typically represented by the fact that as material increases in rate at very, very small strains, you'll typically see a superposition at these lower strains. And so as a consequence, you'll see here that the rates seem to collapse onto a single curve. And that's what's really referred to as the linear viscoelastic envelope. And as you can see, for a linear material, there is very little deviation from that linear viscoelastic envelope. As we start getting branching, you'll see that deviation is this type of linearity, or this deviation starts becoming greater and greater. But as you can see here now, what's interesting, as we increase in rate, particularly at the large rates, you'll get what's a classic behavior for an elastomer. At slow rates, it's able to flow very nice and uniformly. But as we start to increase the rate, this material starts to behave more and more elastically. And as a consequence, it starts to behave, even though it's uncured, it can behave like a rubber band. It'll try to snap back and become very, very elastic. So as a consequence, you start seeing deviations now at these very, very large rates. Now what happens when we start to cool down the temperature? Well, we'll see at 30 degrees Celsius, at the low rates, we'll see again that the material behavior, the tensile stress growth behavior, tends to collapse on a single curve at low strains. But as we start increasing in rate, you'll see that we start getting now a further deviation from this type of linear viscoelastic envelope behavior. And if we go to room temperature, again, this is a very dramatic turn. So not only do we get the type of deformation behavior that we see it just because it's an elastomer, but we get some strange behavior where it now what's called strain hardening. It really starts to strain harden dramatically. And this is typically attributed to flow-induced crystallization. With these materials, we're at room temperature now. You're well within the glass transition temperature of these materials, so as a consequence, it will be susceptible to flow-induced crystallization during deformation. Now, what's very interesting about butyl is if we look at these, as I said before, it is actually a copolymer of polyisoprene, small amount, 2% only, and butylene. And as a consequence, you can see that there is really a combination. It's almost like a composite material. This is represented here in the top upper right-hand curve. And so I've shown now the tensile stress growth curves for a polyisobutylene and a cis polyisoprene. The yellow curves are the cis polyisoprene. The blue curves you can see there are for a polyisobutylene. Now you'll see here that at the elevated temperatures for the butyl rubber, let's say the red curves, for example, for the butyl rubber that's in the lower graph, you'll see that the blue curves, the polyisobutylene, are very, very similar. So you can see here that at elevated temperatures, the material behavior of the butyl compound, the copolymer, tends to be dictated by the polyisobutylene of the material. But as we start decreasing in temperature, you'll see now that 2% component of cis polyisoprene has a dramatic effect. With that massive strain hardening that we see in the butyl behavior at room temperature is due to that small amount of cis polyisobutylene that's present, and we know that's a material that actually exhibits flow-induced crystallization behavior. So again, now we've kind of demonstrated how extensional rheology can be used as an analytical tool. You can see where you can clearly now differentiate even minute amount in terms of polymer content. And as a consequence, this is a very, very powerful method with regard to material characterization. Now let's look at flow from birefringence. Again, as I mentioned, because everything takes place in a fixed plane, we can actually now pass oriented light through that and polarized light through that sample. And in this manner, we can achieve now flow birefringence as we're performing our flow deformation behavior. In this particular case, we're just going to be looking at a white light source. There's obviously more classic cases where you're actually looking at a laser source, but in this particular case, since we're looking at just the overall flow field, it's a much more powerful to look at it with a white light source that we get the full flow field visualization. In this particular case, we're just looking at a white light source that is now separated in between at the SER, as you can see there, where the sample is being held fixed. There are two linear polarizers. So we're passing white light, it's been polarized through the sample, and we're now capturing that image with a digital camera. So as you can see on the curve, the tensile stress growth curve here on the right-hand side of the slide, you can see the classic type of tensile stress growth behavior for this butyl polymer with this massive upturn at the very, very large strains. Now let's look and see what the flow birefringence behavior is like for this material. Now, as you'll see, there's a monochromatic increase in the material, the colors, as we go progressively in deformation. each one of those colors corresponds to a different orientation state due to the flow deformation field that we've imposed on this material. And you can see it's fairly uniform all the way up till we get to these very, very large strains. And the large strains, you'll see the little bit of fringing. Now this is typically because we're going from a perfectly flat geometry to, as we start getting now to very, very large strains, this material is now starting to barrel and start to round off at the edges. So we're getting a little bit of non-uniformity. But this would never be seen unless we're doing an optical type of technique, as we've shown here with flow birefringence. So you can see your flow birefringence coupled with extensional rheology can be very, very, very valuable analytical tool for material characterization. Now let's take it a step further. Now we've taken a sample all the way up to rupture. Now let's do a test, because typically during processing, you're rarely taking a sample all the way up to rupture. If you take a sample all the way up to rupture during processing, you've now, if you're running an extruder, you've lost some of your sample and you have to restart. So it can be a real nightmare. So typically what happens when you're processing is you're taking these materials up to very, very large deformation strains. And you're now, after that deformation, you're allowing the material to relax after that deformation during processing. So what we've done here is we've taken now, for the same material, we've stopped it at various points during that deformation process. Here you can see that it corresponds to different times, but if you can imagine, because they're all at the same rate, in this case a strain rate of 1 reciprocal second, that actually corresponds to a strain of, let's say for the 3 seconds, that's an actual Henke strain of 3. For 2 seconds, it's actually a Henke strain of 2. So we've stopped it now at those various times, and we've allowed the material to relax. Now what's very interesting is if you look at the curves on the left-hand side of the screen, you'll see that the stress relaxation, once the material starts to relax, they actually almost start to come and superpose one another. Now this is very counterintuitive. You would think that, okay, as we're marching up that stress growth curve, which is the black curve you see there, we're locking in morphology because the material is experiencing a flow-induced crystallization behavior. It's crystallized, it's beginning to crystallize with that increased deformation. So it should mean then that we're locking in a morphology, which means now that it should relax slower as it's becoming more and more solid-like. But we're actually seeing the opposite of that. You see that's represented in the right-hand side of this curve, where we see now a relative relaxation. So what we've done here is we've taken the relaxation stress and normalized it by the last stress it saw at the time we stopped the deformation. And you can see here what the relative relaxation is. We can actually see that the actual relative relaxation is larger for the larger strain, and it's smallest for the smaller strain. This is counterintuitive, and actually what we're seeing here now is actually the effect of flow-induced crystallization, and the fact that it's flow-induced crystallization and we're within the glass transition of this material. Those crystallites that were forming during the deformation are actually able to remelt. And as a consequence, instead of it being locked into morphology like you would typically think, because we're still at a temperature where it's within below the glass transition temperature, we can actually see now that we're actually getting those crystallites to remelt. And as a consequence, it's actually achieving a higher state of relaxation with regard to relative relaxation. Now let's look at this visually. Again, this is now flow birefringence measurements, where we've stopped it at various strains. We see a strain of 2 at the far left-hand side of the screen, a strain of 2.5 in the middle of the screen, and a strain of 3.0 at the far right-hand side of the screen. Now let's start the video. And we can see now how, again, the color evolution is very monochromatic. Now, look what happens as soon as we stop that deformation. Look at the fringing that occurs. As a matter of fact, look at what's happening with that material on the far right-hand side. The fringing is actually, it's going much more rapidly. And look at where the fringing occurs. The different colors are evolving in the center. Look, for example, right now at the middle curve. You'll see how it's blue in the center, and it starts now to gradually become blue through the rest of the width of the sample. Same thing now, look at your far right-hand side of the screen. You'll see how it's blue in the middle section, and it'll eventually start emanating out towards the edges of the sample. Now, when you think about a flow deformation, you naturally would think, well, it's got to relax quicker on the edges because it's unsupported. But we're actually saying, no, that's not the case. Because we're able to see these with flow birefringence, we can actually see that it's actually relaxing quicker in the center of the sample. And this is really kind of like we were discussing before because of the fringing. The material is starting to relax any way it can. If you can imagine, it's impinged on the drum surface, so it's kind of anchored there. So now you have an expanse, an unsupported length of sample, and the only way this sample can relax now is coming from flat geometry to now starting to barrel out. And where is it the point from the furthest distance from the impinging points is in the very center of the sample. So you can see here now, as the material begins to relax continuously, the sample starts going from this uniform width to now a more hourglass type of shape. And again, this is now very easily represented because now we're able to do this very nice cessation of extension experiments and couple that with flow birefringence. Again, so we're getting very, very valuable information about material behavior. Now let's take it a step further. As I said before, butyl is a compound that is used almost exclusively in all tires. And it's the compound that is used to entrap air and keep air within your tire. But one of the problems is it's a blessing and a curse in that as you're processing, a lot of times you'll get some air entrapment inside that polymer compound. In this particular case, what we've done is we've actually included a small bubble inside of the polymer sample. So it's the same polymer sample that we've been looking at before, but now we have a very small, well-controlled bubble that's present within the center of the sample. And now what we're going to do is look at two different strains and look how the material relaxes as a function of that bubble being present within that sample. This is coupled with a flow birefringence. So now we can see now what's taking place locally in terms of stress and orientation, which is now a reflection due to the refractive index of the material and the molecules that are changing the white light as it's passing through. So now, on the left-hand side of the screen, we see a hanky strain of 1, where it's where we stopped it, and on a hanky strain of 2 on the right-hand side. So we've stopped it at 2 various strains. One is double the other. Exact same bubble sizes, exact same sample widths. The actual magnification is a little bit different on the video screen, so that's why it looks like it's a different sample sizes, but the exact same sample sizes. Now let's look and see what happens with that deformation. Again, look at the fringing that takes place around the bubble, in particular around the sample on the right-hand side, the larger strain. And look what's happening there. Very stable on the left-hand side, but on the right-hand side, you'll see now what happened is we saw the bubble elongate and become very large. And now the dark line is actually the point at which the sample, that bubble, has forced the material to cleave. It's actually ripped the sample apart. So we've gone now a point of instability with regard to this bubble. And so now we can see, now we have a very unique tool in which now we can see what's taking place locally within the sample as we're deforming it as a result of an inclusion or a void in this particular case. So you could do the same type of measurements with now a solid void. And this is obviously a problem that happens all the time with processing as well, is that sometimes you'll get some little inclusions. Now you can see what that effect can be. And so you can see just dramatically different behavior. Stable bubble on the left-hand side, unstable bubble on the right-hand side. Okay, let's move along now. We've looked at some elastomers. Now let's look at some linear polyethylenes. Now you'll notice I'm focusing on linear materials because when we're talking about flow-induced crystallization, these are the materials that actually can exhibit flow-induced crystallization. Because the linearity of the polymer chains, they can actually achieve a much tighter packing structure, and as a consequence, they are much more sensitive to the flow deformations that we're talking about here, as opposed to highly branched materials where the crystallinity is not nearly as high. So here we're going to look at a couple of different commercial linear polyethylenes. One is a film-grade metallocene linear low-density polyethylene, and the other is a blow-molding grade high-density polyethylene from 2 different manufacturers. In the first case, we're looking at now the metallocene linear low-density polyethylene. And this graph, or these graphs, actually demonstrate the unique capabilities you have with the SER universal testing platform on these rotational rheometer systems. Again, look at the breadth of material behavior we're able to capture, all the way from room temperature, from the top of the blue curves there, all the way down to the fully molten state, which is 150 degrees Celsius, typical processing temperature for these types of materials. On the top graph, we've now superposed the DSC type of behavior, so now we see the heat flow and how this corresponds now with regard to the exotherm on the DSC curves. And as you can see here, the blue curves represent the material when it's still in its solid state. And the red curves are starting now when the material starts to soften and go into the fully molten state. And so in particular, look at what's happening there. You can see that for this particular material, it has a peak melt temperature of 92 degrees Celsius and the onset of melting at 87 degrees Celsius. So these are the areas where you're typically going to see issues associated with flow-induced crystallization. So we're going to focus in that area. Here, this is a classic tensile stress growth behavior for this material in a molten state. So again, a linear polymer. You can see here as a function of the rate. You can see they all tend to collapse on a single curve. You'll see some deviation at the very, very high rates, and that's due to, again, this material starting to behave more and more elastically. Now, particularly as you get closer and closer to the crystallization temperature of the material. Now let's look at a slightly cooler temperature, and we see dramatic behavior, way different behavior. At 93 degrees Celsius, you can see here again that at low strains, we see the material's behavior start to collapse on a single curve. This is the linear viscoelastic envelope. But at some critical strain, we see a massive deviation from this linear viscoelastic envelope behavior. Again, it's a linear polymer. The only other way we would typically see this type of strain hardening behavior is if there's branching present. In this particular case, the reason we're seeing strain hardening is not due to branching. It is due to the flow-induced crystallization behavior now we're imposing on this material. So you can see how it's gradually going farther and farther with regard to deviation as we go to larger and larger deformations. So we're locking in these types of flow deformations. So for example, if you're familiar with going to now to a lower, just 2 degrees cooler, you can see now that the material behavior is fundamentally changing. This is reflected by the fact that the linear viscoelastic envelope tends to be swinging. So it's no longer, so you can see that the fundamental linear viscoelastic behavior that you would typically get with a shear rheology, you'll see that it's actually changing as well dramatically as a function of temperature. But you can see as well the deviations from linearity with this linear viscoelastic envelope is changing much more dramatically. Look at the strain hardening behavior. You can see that it's achieving almost 2 orders of magnitude higher in stress from the linear viscoelastic behavior. Okay, so we're getting some very, very important and unique information that you can't really achieve with other methodologies in terms of material characterization. We're looking at temperatures that are relevant to processing. Because why is this important? Well, obviously for a long time, people in the extrusion game, let's take, for example, people who are making fishing line. People who are making fishing line notice that if we extrude and draw this sample as we're extruding it, we can achieve superior strength with this filament. And this is now what's typically known, obviously to everybody, is this really high tensile or high pound strength fishing line. And the reason for this is they, unbeknownst to them, they didn't really know the science behind it at the time, but really what's happening is they are instigating a flow-induced crystallization reaction. As a consequence of that high degree of stretch they're achieving by drawing the sample as it's coming out the extruder, they're able now to achieve a high degree of orientation and as a consequence build in an anisotropy, very, very high strength in the direction of machining. So you can see here now we have a tool which we can now start looking at what the effects of draw are on extrusion and how does this affect now our end product behavior. Now let's take it a step further. We're going to do some melt flow birefringence now with the SER. And in this particular case, I took a white light source and I'm using a high temperature linear polarizer. So just if you try to do this, mimic this experiment, just keep in mind you cannot use a polarizer from a regular optical lens. Those are usually a film that's achieved some degree of orientation, and as a consequence, that's how they're able to achieve this polarization effect. Unfortunately, if you heat that lens up, it will now ruin and destroy any orientation that was present within that film, and you'll lose any polarization capability. So in this particular case, we're looking at a micro-deposited aluminum grid. If you can imagine a microgrid, a nanogrid that's been deposited on this glass film, this glass slide, and as a consequence, now we're able to achieve a very nice linear polarization regardless of temperature. And then outside of the optical window of the oven, we can capture everything just with a regular linear polarizer on the lens element of the camera. Okay, so now let's take a look at typical stress growth curves for again, another linear polymer. It's a high-density polyethylene now. And again, classic behavior. You look here at the curves, you can see that the DSC curve above shows that we're well into the melting state of this polymer. It's got a peak melt temperature of 129.8 degrees Celsius. And the onset of crystallinity starts at 125.2 degrees Celsius. So again, we're well above the crystallization temperature here. Classic linear behavior for polymer melt. Now let's cool it down a bit. Now this is at a temperature of 128 degrees Celsius, and we can see here that we get, again, very molten behavior still in terms of the stress growth behavior. But let's look at the video. This will help demonstrate it a bit better. You can see, look at how clean the optical image is, the light passing through the sample. It's remaining optically clear throughout the entire experiment. Now we got the clamps coming in through the gap between the two drums. And look at the type of failure deformation mode we have. You'll see it's a very, very ductile failure. It's going to a wispy little thin filament before it ruptures. Okay, this is classic behavior for a polymer melt. Let's go a half degree cooler from there. Okay, just 1/2 degree cooler. Now let's look at the tensile stress growth curve. You can see at the bottom left-hand side of your screen. You can see here what this effect is. You'll see the linear viscoelastic envelope is actually very similar to the stress growth behavior at just a half degree warmer. Again, so we're not changing anything fundamentally with regard to the viscoelastic nature of the polymer melt. But we'll see here now we have a massive strain hardening as a result of the continued deformation. This is due to the flow-induced crystallization. Now, if you look at the curves, you would think, well, this is very obvious. We're obviously seeing a flow-induced crystallization kinetics reaction kicking off right at the point at which we're deviating from the linear viscoelastic envelope, which is a very intuitive assignment. But let's look and see what's taking place now during the melt flow birefringence as soon as we start the flow deformation field. So pay attention closely to on the video screen. Look closely at the left-hand side of the drum, right at the edge, right where you see the clear and the dark within the sample. Now, as soon as we start deforming, look how there's a shadow image. There's a bit of a ghosting now that's taking place there. That's because the light is bending around inside that sample. This is due to the crystallization that's taking place within that sample. Okay? It happened as soon as we started deforming it. Now, look at the type of deformation failure mode here. As we continue deforming it, look at that mode. It looks like it's almost solid. Okay, very, very unique behavior. This is now just half a degree cooler from when we were completely in a molten state. Now let's take it a step further. Let's go a half degree cooler from there. Again, you'll see that there's a massive strain hardening behavior, not a whole lot different in the linear viscoelastic envelope behavior. Again, we're just 1 degree difference now between the green curve and the red curve. But again, now look at the onset of the deviation. It's happening at an earlier strain, okay? So now we're inducing this massive deviation at an earlier strain. Now let's look at the flow birefringence, which is now the video on the right-hand side of the screen. Again, pay attention to the edge of the sample closest to the left-hand side of the drum. It's easier to see it there. But look, as soon as we start the deformation, again, look how it starts to, again, become opaque. It's far cloudier than the sample before. And again, that light is bending around that drum edge. Again, look at the mode of sample failure as well. You'll see it's a real amorphous. You'll see it's kind of solid, it's kind of molten. So again, We've now just spanned 1 degree Celsius, and we've gone from a completely perfectly molten state now to a really unique crystalline, semi-crystalline type of state. Again, now we're able to capture and understand our materials far better than we were able to do before. Again, because of the tools that you're able to use now with these fantastic rotational rheometers that you have at your disposal. So again, this kind of demonstrates some of the unique behavior that's important in polymer processing. But there's obviously other characteristics that are very important as well, but we'll be looking at those here shortly. Now, I always like to keep, when I do these types of seminars, I always like to introduce and look at some case studies. In this particular one, we're going to look at a single case study. I've got a plethora of case studies that I've done in the past, but in this one, this is a really interesting one. And in particular, it addresses some of the age-old questions. If you're not familiar with some of the history behind polymer development, the first polymers that we developed were actually very branched in nature. They're easiest to make. They're emulsion polymers, and as a matter of fact, as a consequence of the polymerization reaction, it's very, very branched type of polymer. It turned out that we had a problem with trying to now control the molecular weight of these polymers. As a consequence, we got a little bit, depending on the batch, we had a larger batch variations at the time when these polymers were being developed, right around World War II, just before World War II. And it was right around that time when we started developing now unique methods with regard to polymerization reactions, and that is now with linear polymers that we're able to achieve in solution. And as a consequence now, we could achieve very, very nice and controlled molecular weights, molecular distributions. Why is this important? Now we can control crystallinity and the end products of our polymers much better by introducing now these solution polymers as opposed to the emulsion type of polymers that we had been producing before. But by introducing these linear polymers, we introduced a whole new can of worms, so to speak, and that now these materials became a little bit more difficult to process. And we'll see that here shortly. So despite being investigated for a long period of time, it's known that linear polymers behave way differently from branched polymers in terms of processability. In particular, this is now some relative demonstrative information with regard to the processing of a low-density polyethylene, highly branched polymer system. And you'll see here two important things. First of all, look at the left-hand side of the curve on the left-hand side of the screen. And you'll see here that we see a classic, what's called an apparent flow curve. And what you're basically plotting here, if you can imagine, is the driving pressure as a function of the flow rate. Apparent shear rate is really just a function of the flow, the throughput that you're passing through the die, and now you're plotting that versus the driving pressure that's being monitored as a function of you trying to push it through the die at a fixed rate. If you look at it, it looks like a continuous curve. Looks like a monotonic increase. Again, keep in mind this is a log-log scale, so it's actually a power law type of curve. So this is what you would consider a classic power law type of behavior with a polymer with regard to processing. But look at the extrude now. You'll see images on the right-hand side of the screen which demonstrate what the extrude looks like as it's now passing and exiting through the die. And you'll see here we go from a very smooth extrude to now, as the material starts to show a very gross or distorted appearance as we go to higher and higher and higher rates. Okay, very classic behavior, and as it turns out, you start seeing this little introduction. It doesn't start off as a really gnarly type of melt fracture, what's it referred to, until you get to very, very high rates. But you'll see here at very low rates, let's say, for example, you'll see there at a rate of 100 reciprocal seconds in shear rate, you'll see that the polymer starts to go from a smooth to now this, periodically you'll see just a little, it's like a little twist in the polymer sample. And so now this is a gross melt fracture that's occurring within the sample. It doesn't really occur with a whole lot of periodicity, but it does start to appear in the extrude. Now let's look at a classic case for a linear polymer. This is now a linear low-density polyethylene melt. And we'll see here that, first of all, look at the apparent flow curve for this material. Way different than what you saw for the branched polymer. In particular, you'll see there's a discontinuity in the flow curve. Now we're plotting again, if we're driving it as a function of, we're controlling the throughput through the die, and we're monitoring the driving pressure as a function of that throughput. And you'll see here that we get two distinct branches of the flow curve. You have a lower branch, and then at the higher rates, a second branch that's occurring there. So it's a discontinuity. And what's happening in between there is in a phenomenon known as a spurt effect. So we're going to a stick slip is what it's also referred to as well. And this is now typified by the fact that in this stick slip regime, as you can see on the images on the right-hand side of the screen, the material goes from a semi-smooth to a rough type of behavior. And you can see here as well, at rates just before that, we get a phenomenon known as shark skin melt fracture, which is typified for a very periodic deformation and looks like a little bit of a fracture, just a surface fracture along the extradate as it's exiting the die. Again, slightly higher rate, it starts going to the stick slip. Now, if you're familiar, if you've ever seen this phenomenon, on a capillary, for example, easiest way to show that in a laboratory, you have a capillary rheometer, you're pushing material at a fixed rate, and what you'll see now is when you enter this stick slip regime, you'll see that the pressure starts going through some oscillations, okay? It'll go through a stick, slip in terms of pressure. It's trying to grab, then it just spurts through, grab, spurts through. And this is now being typified by this smooth and this corrugated or rough type of appearance, typically referred to as shark skin melt fracture. Ultimately, at higher rates, again, you get gross melt fracture, which is just unavoidable for many of these polymer systems. Again, this has been well known for a long period of time. Linear polymers behave way differently from branched polymers, and so you can see that's just completely different ball of wax here with regard to material behavior. Okay, so now that it's being said, although many efforts have been successful in manipulating processing behavior, an age-old question remained unanswered at the time. So really, just to kind of back up a little bit, it was discovered back by the folks at DuPont that this happened a long time ago when they were still developing Teflon material, their Teflon product. They were using the exact same extruders that they were using for their polyethylene lines, which is, again, a big product of theirs at the time. And after running some Teflon through the extruders, the typical modus operandi, if you're familiar with extrusion in pilot plants, is you flush out the material that you just finished extruding to a material that's well known, and in this manner you know when you're getting back to a flushing out of whatever material was trapped within your extruder. Well, what they found is that after processing and pushing Teflon through the typical purge material they use as a polyethylene, after running that Teflon for an extended period of time, they ran polyethylene. And to their amazement, they found that this linear polyethylene that they were running through there wasn't showing any shark skin melt fracture. And this was really alarming to them. They had no idea what was taking place there. Eventually, with enough of a time of extrusion, eventually the shark skin reappeared. And what they didn't know was they essentially had coated the die at the time with the Teflon. Teflon actually promoted a slip layer, if you can imagine, at a different velocity. So instead of it being a zero velocity at the wall, if you think of classic fluid mechanics, your parabolic type of flow field as you're passing material through a die or an orifice. And what was happening is that they were actually getting a non-zero now condition at that boundary. And as a consequence, they were able to reduce the stress that's taking place on that material vis-a-vis the fact that we're creating a slip layer due to the Teflon that was present on the die wall. Eventually, the die wall pushed out of the way, and the polymer was able to readhere to the die wall, and as a consequence, they got the shark skin melt fracture again. So again, these are types of phenomenological behavior that's been observed for decades in the polymer industry, but it wasn't only until recently that we started now seeing the fundamental mechanics associated with what are the mechanisms associated with these phenomenological effects that we've observed in the past. So again, some of these age-old questions: why does stick-slip flow occur only with linear polyethylene? And that's what we're going to be typically I go with a more involved case study, but in this particular case, we're just going to be looking at why does stick-slip occur for the linear polyethylene and not for the branched polyethylene. Okay? So here we're looking at 4 different commercial polyethylenes. One is a coating grade low density polyethylene, highly branched, low viscosity. Look at the melt index, it's 7.5, which is what you expect from a coating grade. You don't want it to be a very high melt index material because you want it to flow and be able to coat whatever you're trying to, whatever substrate you're trying to coat. The other materials we're looking at now are a film grade linear low density polyethylene. You can see the melt index is much lower. There's a film grade low density polyethylene that we're looking at as well, and a film grade metallocene linear low density polyethylene. And so what we did here is we're doing a rheological characterization. So as any good rheologist, we're going to use the tools that we have at our disposal. In this particular case, we're going to start off with shear rheology. Then we're going to look at the processing behavior with capillary extrusion. Then we'll look at the extensional flow behavior with the SER. And ultimately now we'll characterize the dynamic melt adhesion behavior with the TPL measurements with the SER. Very unique methodology now you can use as a function of the fact that this SER now is really a universal testing platform. So let's start off with our good friend, shear rheology. And what does it tell us? Well, we've got 3 graphs that are presented up here. So a typical rheologist would look at a couple different things. First off, they'd look at perhaps a step shear. You're doing a step shear trying to get the shear relaxation modulus of the material. This is now not run as often as the types of curves you see now on the right-hand side of the screen, which are your dynamic modulus, dynamic shear modulus, which is your G prime and G double prime, which are really the sine and cosine Fourier transforms of the shear relaxation modulus. As long as you're in the linear viscoelastic regime, you're getting the exact same information. It's just now you're looking at an oscillatory type of time domain, frequency domain, as opposed to a time domain. Okay? So we're essentially getting the same type of information from these curves. And again, we get some relative information with regard to viscosity, which is understandable. And what do we see? We see that the coating grade, which is the red curves, have the lowest viscosity, particularly at the low rates or low times. And as we now start going at these very large, you can see when you look at shear relaxation data, low times correspond to rapid deformations. Long times correspond to very slow deformations, okay? And so you can see here that that's where the analogy is in these curves, from shear relaxation modulus to jumping to the frequency domain. Again, we get some interesting information, maybe some information with regard to molecular weight, molecular distribution, certainly viscosity, but really we can't differentiate what is to a breadth of molecular distribution. Let's say we have a linear polymer, perfectly linear, but there's a number of different size polymer chains present within that polymer, that batch of polymer. And as a consequence, a lot of times having a very broad molecular weight distribution polymer, linear polymer, can look very similar to a very branched polymer. So it's very, very difficult to see in shear oftentimes. Now let's look at capillary extrusion for these 4 polymers. Again, you can clearly see the 2 linear polymers and the 2 branched polymers. 2 branched polymers have a monotonic increase in the apparent shear stress as we're plotting apparent shear stress versus apparent shear rate, or if you'd like, driving pressure versus flow throughput. And look at the 2 linear polymers, which are the yellow and the green curves. First thing you'll note, big discontinuity. Classic behavior for a linear polymer. We see it with the linear polymers, not with the branched polymers. And I've also now put some critical shear rates for the onset of these types of behaviors from shark skin. Again, usually the branched polymers don't exhibit a shark skin. They don't exhibit stick slip. They do exhibit a gross melt fraction. Typically, you see that it happens at a much earlier onset with regard to shear rate. But again, very, very different behaviors. Now, as we look at an extension, even though we didn't see a whole lot different in shear rheology, we see massive difference in extension. And again, this is really the only way to differentiate clearly between linear polymers and branched polymers. So let's look at these separately here. So on the left-hand side, we see the curves in extension, the tensile stress growth curves for the 2 branched polymers. Red curve is for the coating grade, again, low viscosity. Blue curve is for the film grade, low density polyethylene. You'll see that, again, look at the linear viscoelastic envelopes, the curves in which now they deviate from the strain hardening behavior, those base curves. You'll see that they come to 2 different levels. And again, that's a reflection now. As you get to the larger and larger times, that actually where it starts to plateau is actually 3 times the zero shear viscosity material. So you're getting this very important information, very, very low rate deformation behavior from the linear viscoelastic envelope that you're able to achieve in tensile stress growth curve. And, but you'll see here that even though there's a very fundamental difference between those two curves in the linear viscoelastic regime, look at what's happening in terms of strain hardening. The red curve, which is the much lower viscosity material, is achieving the stress level almost of the blue curve, which is the film grade low density polyethylene. Again, so this tells you that we have now fundamentally different type of branching behavior or branching that's present in terms of the architecture of these two polymer systems. Now let's look at the two polymers on the, this is now further represented here in these curves. More clearly you can see on this slide. But look at the, again, you're able to achieve now a stress state that's almost just a little bit lower with that coating grade as opposed to the film grade polymer, even though there's a way bigger difference in terms of the shear rheology and shear viscosity. Now let's look at the linear polymers. Linear polymers at very slow rates, pretty much kind of superposing on top of one another. Very similar melt index behavior, very similar type of shear rheology, but it's not until we get to the very, very high rates that we start seeing now clear differences between these two different types of polymers. This green curve is for Ziegler-Natta, classic linear low density polyethylene, and the yellow curves are for metallocene type of polymer. And you'll see here that as we start to increase in rate, the deviation from the linear viscoelastic envelope is much larger for the metallocene polymer. It actually starts to behave more and more like an elastomer than it is a linear polymer melt. So again, we can see now subtle differences in material behavior that are really impossible to see in shear, but we can clearly start differentiating, particularly at these rates that are relevant to polymer processing. So now we're starting to answer a lot of these age-old questions. Why does one linear polymer behave differently from a linear polymer, another linear polymer, and inherently, why does a linear polymer behave way differently from a branched polymer? Now, I'm going to introduce now a new concept, which is now looking at these materials in peel mode. Now we're trying to look at what the effect of work of adhesion is on these different polymer systems. Everything we've looked at so far has been an actual deformation of the material itself. Here we're looking more phenomenological effects. Now that is the work of adhesion of a material against a different substrate, having to deal with now the surface energies of these materials. In this particular case, what we've done is we've taken a polymer and we've sandwiched it in between two substrates. And we've taken the ears of the substrates, we've wrapped them around the securing clamps of the SER. And this is actually a picture of our original SER system, which is different from our more recent models, which has the detachable drums. These actually have the fixed drums, but works the exact same way. But the idea here is that we're able now to achieve a very nice T-peel type of geometry where we take a sample and we're now trying to separate it apart, okay? One ear is attached to one side of the drum and the other ear is attached to the other drum. And this way we're kind of peeling it and splitting it apart, if you can imagine, but while it's all in the molten state, okay? Now let's look what that peel behavior looks like. Okay, let's start off with the film grade low density polyethylene. In this particular case, we see some interesting behavior. Now, I've kind of, you can see there's different types of symbols, and these correspond to the type of failure mode that was observed during the peeling process. And what I've plotted here is peel strength versus peel rate. It's on a log-log curve, kind of similar to what you would plot in terms of an apparent shear stress, in terms of, let's say, the driving pressure versus throughput rate. Okay, so now we're trying to relate, if we can, if it's possible, to relate the work of adhesion in a similar manner to what we'd have in terms of throughput, driving pressure, and the rate of flow through the die. So what do we see? We see actually two different slopes of a curve, but it's monotonically increasing. I mean, it's always increasing in rate. So as we increase in peel rate, it's always increasing in peel strength. It's important note to note that. But look at the type of mode it transitions from. At the lower rates, okay, the round dots, it corresponds to a purely cohesive failure. This is now the material, if you can imagine, is still adhering to the substrate and it's splitting right down the middle, okay? Which is what you would expect. At very low rates, you're now trying to deform the material, and what you're doing is actually, you're trying to get actually a material deformation within the center of the sample, and it's splitting right apart. That happens up to some kind of critical rate. At a critical rate, let's say beyond 1 reciprocal second, or actually 1 centimeter per second, we actually see now transition from this purely cohesive failure to that of a porous type of failure. Now, if you look at it, when I say porous, if you look at the substrate afterwards, after you've finished the experiment, it almost looks like a sponge. You've created these little voids within the material. So very interesting. As opposed to splitting it right down the middle, we know we're going down to some elevated rate, to now where it's starting to become unstable, this type of deformation. And what happens then, at an even higher rate, we went up to actually 100 centimeters per second. So we're talking 1 meter per second in rate. These are rates that just can't be achieved on an instron, okay? You see here that we get a purely adhesive failure. If you look at the substrate after the test, you don't have any evidence, at least visibly to the naked eye, that there was ever any polymer on that substrate. Very interesting behavior, but look, we're always seeing an increase in our peel strength. So as we increase peel rate, always an increase in peel strength. Now let's look at the coating grade. Very interesting behavior. Again, lower viscosity, it's a coating grade after all. It's got a lower melt index, so do we expect. At low rates, we get a lower peel strength. That's exactly what we see. Again, we get this very classic type of cohesive type of failure at the low rates, but then as we start increasing in rate, we get some very interesting behavior. The peel strength exceeds that of the film grade low density polyethylene, even though it's got much lower viscosity. Look at the difference in viscosity here. So it's more than a factor of 2 or 3. And it's amazing that now we're getting a higher peel strength with this lower viscosity material. And look at the type of failure mode. We went up to 2 meters per second in different peel rate. And it never deviated from that porous type of behavior. It never went purely adhesive. This goes to show you why this material is an effective coating grade. It's actually coating onto the substrate you'd like it to. It's not being removed easily. So again, a very good experimental method to understand why or how a material can be a good coating grade as opposed to a film grade. Again, these are very, very unique tools that we're able to look at as a consequence of the development of the SER. Now let's look at, again, but keep in mind, increasing peel rate, increasing peel strength. Now let's look at the linear polymers. First of all, let's look at the Ziegler nanopolymer. This is the linear low density polyethylene. Again, at the lower rates, purely cohesive failure, it's actually just slightly higher, even though it's got a much higher viscosity than the film grade low density polyethylene. You actually see that it has a lower peel strength, and just that slightly bigger than the peel strength of the coating grade. And again, purely cohesive failure, but what happens at some critical rate? We start seeing an instability. It's actually a stick-slip, cohesive to adhesive type of instability. So again, for a constant rate, we're seeing an oscillation in the peel strength. As the material tries to deform or tries to fail cohesively, we see it delaminates, and then it tries to fail adhesively, cohesively again, then it delaminates. Same thing that we kind of see in extrusion. Now, and you see there's 2 different tracks, complete different tracks in the peel strength curves. Again, I can't stress this enough. For the longest time, we as scientists and rheologists have been trying to understand this phenomena. We were trying to understand this phenomena of stick-slip. We didn't really have any other method to characterize stick-slip. You couldn't do it in cone and plate. You couldn't do it in these other types of traditional shear rheology types of methodologies. And the only way you could do it was the capillary extrusion. Now we have an independent way of doing it. We can now measure the dynamic work of adhesion as a function of surface energies. Look at different substrates, different thin films that we're now placing against these polymer melts. Very, very unique tool. And again now, what's interesting is we see a drop-off, and after we see, from that stick-slip instability, we see a second, like a trough, and then it starts increasing again. Real clear and distinct. So unlike the branched polymers, which saw with increasing rate always saw an increase in the peel strength, the linear polymers beyond a certain rate, it goes unstable, and then it's complete delamination after that. So even though it's complete delamination, look how the peel strength just continues to go up. Okay? Very interesting behavior. Now let's look at the metallocene polymer. Very similar behavior. Look at the peel strength at low rates. Very, very similar behavior to the Ziegler-Natta polymer. But now look at the point of instability. Look at the range of instability. Okay? Very large. It's much larger than the Ziegler-Natta polymer. And if you recall from the flow curves, there was a big jump in the low shear rate flow curve versus the high shear rate flow curve. What do we see here? A big jump in this big region of instability with the metallocene polymer that we didn't see with the Ziegler-Natta polymer. But again, it shows very similar behavior in that we have a completely second track of the peel strength curve. And again, unlike the branched polymers, we see it's a monotonic increase, then boom, it goes to an instability, stick, slip, stick, slip, stick, slip, and then it's complete delamination. And we can look closely at this. This is the typical peel trace now for that metallocene polymer, the yellow polymer. This is at a rate in which now we're actually seeing purely cohesive failure. This is at a rate of 0.3 centimeters per second. At a slightly higher rate, and this is actually double the rate, 0.7, you see that it starts up the same kind of curve in terms of the peel strength. It goes through a peak and then drops down. Goes through a peak, drops down, so on and so forth. And it turns out that if you look at that, the actual peel specimen after the peeling experiment, you'll see that those peaks in the peel strength curve correspond to the peaks that occur on the actual sample itself as it was trying to delaminate. And you see what's very interesting is that the material is trying to fail cohesively. It goes through and it builds up stress, but it can't sustain that stress. So what happens? It fails. It fails at the only place it can, which is the weakest point, the substrate, which is right at that interface. So it fails there. It regains strength like a coiled spring. You're relieving string, coming back, coming back. Just like the pressure oscillations that I've shown on the right-hand side of the screen. Those are the pressure oscillations you would see during stick slip and extrusion. Again, so this is now independent method of characterizing a phenomenon that up until this point in the laboratory could never be generated other than with capillary extrusion. And we're getting very fundamental information. We're able, with one device now, we're able to couple everything with regard to extensional rheology, which is playing a vital role in all of the gross melt fracture and the shark skin melt fracture. And now we're seeing now the effect of the work of adhesion, the surface energy effects between the polymer melt and its substrate, its interface. As we go to a higher rate, we see again stick, slip. But then even higher rates now, 10 centimeters per second, we see now the material tries to fail. It tries to fail cohesively, then boom, it just gives out. And look at, for 3 centimeters per second, 10 centimeters per second, look at the level it comes down to. It's almost a constant type of peel strength until it starts bringing up now and starts increasing again. So again, complete delamination. When you look at the sample, even though it was molten, I mean, try taking molten polymer off any kind of substrate. It's very difficult. And you look at the substrate afterwards, there's no visible evidence that there was ever any substrate on that, or any polymer on that substrate. Okay, so now we have a very unique way of characterizing and for the first time fingerprinting processing behavior between linear and branched polymers. Again, look at that. If you look at the curve on the right-hand side, that's just the pressure versus flow rate curve, and you'll see the big jump in the yellow curve. And what do we see on the peel strength curves on the left-hand side? Big jump, big unstable region where it goes stick, slip, stick, slip. So again, we're getting some very, very unique information, stuff that it typically you can only see during extrusion, but now we're starting to put science to what is observed phenomenologically out in the processing field. Okay, what's up next? We've seen everything up to this point has been for the universal testing platform, the SER universal testing platform. And that featured, as you recall, 2 counter-rotating drums. One of the limitations with the counter-rotating drums is that you can see that as the sample starts to overwrap the clamps or overwrap the sample, you can basically run into problems now if you're no longer controlling the strain deformation accurately. As a consequence, you're typically limited in terms of the upper level, in terms of Henke strain, to about a Henke strain of 4, which is fine for many polymers, but for many linear polymers, they can survive well beyond a Henke strain of 4. And so it's nice to be able to go to much higher strains. Well, coming in the first quarter of next year, we'll be launching the new SER4. That is now the device which actually introduces a co-rotational drum configuration. So instead of laying the sample across the surface of the drums, we now have the situation which now it's actually being tied in between the drums, as we can see here in this video. So you can see here as we rotate co-rotationally, we now have minimized L, which is now our unsupported length of the sample. But for one given revolution, we're able to achieve almost double the Henke strain that we're able to achieve with the counter-rotational configuration. Okay, so very, very powerful method. We're real excited about it. And again, this will be used exclusively as an extensional melt device. Obviously, you can't do peel experiments or tensile type of behavior here. There's really no need to for tensile type behavior because nothing will survive to these Henke strains of 7 or greater. So again, very, very powerful method now for melt rheologists. Now let's look at some classic curves here. Everything that we showed for the counter-rotational type of drum configuration, we can actually demonstrate for the co-rotational configuration, but we can achieve much, much larger strains. That's demonstrated by the fact that in the lower corner of the slide, in the lower right-hand corner, you'll see here that we were able to achieve easily Henke strains of 6 for this polymer melt. In this particular case, it's the highly branched material. So we can go well beyond what would typically, we'd have to stop a test at a Henke strain of 4. We can go beyond that point and we can see what happens. And you can see for the most part that it starts to achieve somewhat of a steady state. It may come down a little bit right after that peak, but we can actually go to much, much larger strains than we were able to achieve before. So we're real excited about this technology coming up. So that being said, I'm glad you were able to share your time with me today. In summary, because of the strong flow fields that we're looking at, and we're able to generate with this device, the SER technology, we can look at things that are very, very sensitive to flow-induced crystallization effects in linear polymers, as well as polymer macrostructural effects in highly branched polymers as well. Even the subtle degree of polymer difference. In these systems we're talking about copolymer systems, we can actually see differences in microstructure. If you recall from the butylene, the butyl rubber composite, which is the polyisoprene with polyisobutylene, you can see here that we can see even with 2% of polyisoprene, we can see clearly the effects of what contribution that 2% of polyisoprene has to the overall bulk rheology of the butyl rubber. Again, I think that hopefully your takeaway from this, hopefully, is that you can see that extensional rheology is a powerful method for material characterization. In my opinion, there's nothing in the rheological realm that really comes close to the breadth of material characterization capabilities. And by having a device now that fits so cleverly on these beautiful instruments that are made, these rotational rheometers, they're fantastic. You can do everything on a very small scale. Great temperature control of rates that, that's unachievable with other material characterization systems, and torque sensing and load sensing capabilities that are just not achievable. In a typical strain gauge type transducer, you get maybe at tops three decades of range here. You're going well beyond that with these types of rheometers. So fantastic piece of equipment, and all we're doing now with the SER is unleashing the full capability of these devices. So you can use your device the way it was traditionally intended to, which was in shear, but with the addition of this SER technology, you can unlock the full potential of these fantastic systems that you have at your disposal. That being said, I thank you for your time, and I'll be willing to entertain any questions if you have them. Thank you.
Thank you, Martin. A recorded version of this presentation will be archived and available through the TA Instruments website.